Okay, so as promised last time, we can now use all of this stuff of the standard representation and the field polynomial to define some invariants for algebraic numbers, which I'm going to call the norm and the trace. So here's our section 1.7. This is the last section of chapter 1. That's called norm and trace. This is going to give us invariants, but it's also a way of taking numbers, algebraic numbers, and obtaining from them, say, an integer or a rational number, which will be somehow tell us something about the algebraic number that we had. So, as always, we start with a definition. 1.71. I'm going to let this work over fields over Q. So let K over Q be a number field. And alpha some number in K. Then we define the norm and trace. So the norm of alpha by, let's denote it like this, norm K over Q of alpha. This is going to be the determinant of A of alpha. This is going to be some number in Q. Maybe I should just be precise and write this determinant in Q. Remember that we said that this matrix depended on where I took my basis over, and I was going to ignore putting the Q's here, but just to be precise, this is why I have K over Q. See, and you can, similarly, if you're taking this to be some field F, and you put this field F here, then you get the norm of alpha from K over the norm from K to F of alpha be the determinant of that matrix, which would now be an element of F. Anyway, you can imagine how this generalizes if I just change Q to F's everywhere, and it works. So this is the norm and the trace. So trace of alpha by, so that's going to be this TR K over Q of alpha. This is going to be defined to be, this is defined to be, this is what the symbol means defined as. It's defined to be the trace of A of alpha, which again, okay, I should put the Q's again just to be, which is amount of Q. Here, let me just remind you, trace of a matrix is the sum of the diagonal entries. This is the sum of that. You write your matrix and you just go down the diagonal and add up the entries. And this is what the trace of a matrix is. So let's go back and look at this example that we had before. So example, let K be Q square root 5, and we'd taken alpha to be 3 plus 2 root 5. Then we saw that A of alpha in this basis, in this obvious basis, the 1 root 5 basis, this looked like 3, 2, 10, 3. Therefore, to the norm K over Q of alpha, this is just the determinant of this matrix, which is, you'll find this is minus 11, and the trace, this is just the sum of these diagonal entries, which is just 6. Great. So how does this norm and trace relate to the things that we were looking at before, like this field polynomial? So here's a proposition, 1.7.3. K be a number field. Of degree n over Q, i.e. in symbols K to Q equals n, and I'm going to take alpha to be some element in K. Then the field polynomial Cx of alpha knows about the trace and the norm, this is x to the n, this is the characteristic polynomial is always harmonic. The next coefficient, well, minus of the next coefficient, this is k over q of, this is the trace. So that if you look at the coefficients of x to the n minus 1, then minus it is the trace. And you have a bunch of other entries, and then the last one is going to be minus 1 to the n, the norm k over q of alpha. So you got to be careful with these signs. Make sure. So a lot of times, it's the easy way to compute the norm of the trace is to compute this field polynomial. And then from that you just pick out the norm of the trace by looking at the last coefficient and the second coefficient. But you got to make sure you get the signs right. That's usually where people make small mistakes. The proof of this, well, this is something that usually you should have seen in some previous algebra course, but I'll give you the result. So I'd say recall the following result from linear algebra. If you haven't seen it before, then this is the first. This is, take this as a given, which says if M is an n by n matrix with characteristic polynomial, say c of x, then c of x is going to be x to the n minus the trace of m, x to the n minus 1 plus minus 1 to the n, the determinant of m. So this is some result of from linear algebra. If you look at if you find a characteristic polynomial of a matrix, the last entry of it is going to be the determinant up to some sign, and the second coefficient here is going to be the trace of your matrix. But if you use this and you combine it with our definition of what the norm and the trace were, which were to be the determinant and the trace, then you see that if I take C of alpha, the trace of alpha is meant to be the trace of the matrix, and this is meant to be the determinant of the matrix, and yeah, so we get the result. So using this, the result follows at once. Great. Now, what else do we know about this norm and this trace? So here's another proposition, 1.7.5. So let K be a number field, and take two elements alpha and beta and K. Then we'll see the trace is linear with respect to addition, and the norm is multiplicative with respect to, well, with respect to multiplication, i.e. then we have the trace from K over Q of alpha plus beta. It's the same thing as the trace K over Q of alpha plus the trace K over Q of beta. So we have this, and the norm alpha times beta. This is the norm of alpha times the norm of beta. Okay, so let's prove this. So by definition of this trace and this norm, we only need to consider the trace of this, A alpha plus A beta, and the determinant A alpha times A beta. But we know from linear algebra the trace of the sum of two matrices is the sum of the traces, and the determinant of a product of two matrices is the product of the determinants. But we know, say, from linear algebra, that if, say, M and N are two n by n matrices, then the trace of M plus N is the same thing as the trace of M plus the trace of N, and similarly the determinant of M times N is the same thing as the determinant of M times the determinant of N. So the result follows. Just so we're done. So here's the next result. Tells us how norms and traces relate to the embeddings and to some of the results that we were proving from last time. So another proposition, 1.7.6. Let K be a number field. And alpha some element in K, and let sigma i's be the embeddings of K into the complex numbers. Then we have the following: the trace K over Q of alpha is just the sum over I of these sigma I of alpha, and the norm K of Q of alpha is just the product for I of these sigma I as of alpha. So if you want to find the trace of an element, if you know all of its conjugates are, then just add them up and that gives you the trace, and the same for the norm. If you want to find the norm of alpha, but you know all of its conjugates, then just multiply the conjugates together. So this is another quick way of computing the norm and the trace. So proof. So now recall, so here's again another result from linear algebra. Recall that the norm and trace of a matrix, the determinant, say the determinant and trace of a matrix is invariant under change of basis or under conjugation. Therefore, take the trace K over Q of alpha is the same thing as, well, the definition is the trace of A of alpha, which is the same thing as the trace of something like P to the minus 1 A alpha P. Similarly, for the norm, now just recall that we just proved something, well, last time we proved something about making A alpha diagonal or not by finding some P. So now by proposition 1.6.7, we see that we can find some P such that P times 1 A alpha P is diagonal with entries sigma I of alpha, and then once we know this, then the result follows. Okay, and the last thing I want to highlight from the norm and the trace. So we're going to use this a lot later for studying algebraic numbers, algebraic integers. By understanding the norm and the trace, you can prove a lot about what these numbers have to be. So computing what these numbers is useful, but there's something extra that the trace gives us, which is a bilinear pairing, which is really useful. So just write this here. Using, I'll just say not, the trace also gives us a Q bilinear pairing, defined as follows. So its definition 1.7.7. Let's take our number field. So we have a pairing. So I'm going to denote it like this. Just going to go from k cross k. So this is the Cartesian product of k with k to the rational numbers given by defined as follows. If I take 2 alpha and beta, this is the same as a trace k over q of alpha times beta. Remember that trace, this isn't a trace of alpha times a trace of beta, because trace is only linear with respect to addition, not with multiplication. So this is actually something different. And okay, let me just remind you, Q bilinear pairing. So this just means that if I had like A plus B and C, this is the same thing as AC plus BC, and then you can pull out factors of Q from it. So if lambda is in Q, then lambda A B is the same thing as lambda A times B. Just to remind you what Q bilinear pairing. So this works obviously if the sum is either on this side or on this side. It's bilinear because it's linear in both variables. Okay, but this isn't just a Q bilinear pairing. It actually satisfies something stronger. So here's the proposition. 0.7.8. This is okay. This is called. I forgot to give this a name. This is called the trace pairing. So what the proposition says is that the trace pairing is a Q bilinear perfect pairing. In other words, what does the perfect mean? If you have alpha and beta in K and lambda in Q, then well, okay, we've already said this. I already wrote this bit. So this is the same thing as alpha lambda beta, same thing as lambda beta. And if I have some alpha in K such that alpha of beta equals 0 for all beta in K, then alpha has to be 0. So if I have some element which pairs with every other element to 0, then the element that I started with, alpha, must have just been the 0 element. This bit is what perfect means, and this is part of it being Q bilinear. So what's the proof? So the fact that it's bilinear follows from the definition of the trace K over Q. We checked that the trace was linear, and so just go back to the definition. Imagine if I replaced alpha plus to be like gamma plus delta or something. So you do change it to a gamma plus delta and then expand it all out and figure out what the trace is. You'll see that this just follows immediately from the definitions. So just the hard bit, or the thing to maybe think about a little bit, is to check that it's perfect. Perfect. Consider some alpha different from 0. Then, because we're in a field, alpha to the minus 1 is in K. Therefore, the trace from K over Q of alpha times alpha inverse, this is the same thing as the trace K over Q of 1, which if you run through the definition, you'll check that this is just a number, an integer, and it's just going to give you the degree of the field, which is non-zero. Non-zero. So the trace of a non-zero element. So, okay, so, yeah. So, for me to check that it was perfect, I have to check that if this wasn't to be perfect, I would be able to find some beta such that alpha and beta, when I look at the pairing is 0. But for no matter what alpha you give me, if I take an alpha which is non-zero, if I just take beta to be alpha inverse, then this trace, so maybe I should write this here. Therefore, this thing, which is by definition, is this. This thing, which is this trace, is some element which is non-zero. So for every alpha that I take, as long as it's non-zero, I can find some beta such that alpha beta is non-zero. So this proposition, this has to hold. So we're done. And we're going to use this will show up later on in technical proofs. This trace pairing, this perfect pairing will be useful later on. But this ends our chapter 1 on number fields and so on. Now we're going to somehow refine ourselves from not just looking at all algebraic numbers, we're going to refine ourselves to algebraic integers. And this is where, instead of working with fields, we're going to start working now with rings. And this lets us work with ideals and all of this. So like the main bulk of the course is not going to look at these things. But that will be part of chapter 2. But this is the end, also right here, end of chapter 1.